Good morning, everyone, and welcome to lecture 16. So, we are going to continue with finding the time rate of change of various quantities. So, in the last two classes, for example, we introduced velocity gradient tensor. We found the time rate of change of length of line elements, time rate of change of orientation of line elements, then time rate of change of angle between two line elements, and let me work out today the rate of change of volume. Okay, so we had seen earlier that dvy, that's equal to j times dvx, isn't it? So dvx being undeformed infinitesimal volume element and dvy being the corresponding deformed volume element, and they are related through j, where this j is determinant of f, right? So we have seen this already, and so let's try to find out its time rate of change. So obviously, then we have to take the time derivative here. And remember, we are doing material time derivative. So dvy dot is then j dot times dvx, and you don't take the derivative of dvx because that's a constant. Now, what is j dot going to be? So j being determinant of f, the j dot, it turns out to be, so there is of course a lengthy derivation which shows that j dot is equal to determinant of f into trace of f dot f inverse. Okay, it comes from a lengthy calculation. So now determinant of f is same as j, so you can write it as j times trace of, and look inside, that's L, big L, isn't it? But big L being the Eulerian velocity gradient, and then you are looking at trace of that big L, right? So we can also write it as j times divergence of velocity, isn't it? Which is also written as j times gradient respect to y dot with velocity. So see this one for example. So L is del V over del Y, and then trace of L, if you write in component form, then trace of L is simply del Vi over del Yi, right? And this is also then the divergence, no? Divergence of velocity. So that's what I wrote down here. Okay. So that means we have already this formula, and we can say then that dvy dot, that's equal to j times divergence of velocity into dvx. So that's our relationship. And notice, if you want that the deformation is such that volume is not changing with time, there is no change in volume with time, then you would like that the right hand side becomes zero, right? For isochoric deformation, basically. So for isochoric deformation, so isochoric means no change in volume. dv y dot should be equal to 0. That means j times divergence of velocity should be equal to 0, which further implies that the divergence of velocity itself is 0, isn't it? Because j is never equal to 0. And I guess this is something the people from fluid mechanics can relate. Whenever you have incompressible fluid flow, then you always have this accompanying equation that divergence of velocity is equal to 0, right? So for it's a practical example that incompressible fluid flow, you have this case. For an incompressible solid, you have simply that J is equal to 1 for incompressible solid, right? Then only the volumes are not changing, J equal to 1. And as you take its time derivative, you will get the divergence of V equal to 0. Okay, I hope you are able to relate this with whatever understanding you have. So that being the change of volume, rate of change of volume, the thing which is remaining is, for example, rate of change of area and the normal to the area, right? But this is something I'm not going to do. But this is a probable question for minor examination. So try to work it out on your own. Okay? Rate of change of area and normal to the area. How these two quantities are changing with time. All right. So you can see the importance of velocity gradient, isn't it? It's showing up in rate of change of all the strain quantities. Even in the rate of change of orientation, it's the velocity gradient which is showing up. When we are talking about strain, then what we had was u, right? Or u square showing up in the formula for longitudinal stretch, or in the formula for change in angle, or in change in volume. It's u or u square that's showing up there. But here, when you talk of rate of change of those quantities, it's the velocity gradient which is showing up. Okay, so they are very important quantities. Any questions so far? Okay, if there is no question, then let me work out an example. And this is something which you guys are already familiar with, this example. So let's talk of simple shearing motion. Okay, and we have already seen this example. So according to this, y1 is equal to x1 plus some k of t. So k is changing with time into x2. Then y2 is equal to x2 and y3 is equal to x3. Okay, and physically you can notice that this is actually shearing. So at any time t, this is how the body would have deformed, right? So this is the region occupied at time t, and this thing, that's your k of t. Okay, so Well, I think I made a mistake here. So if this is theta, then tan theta turns out to be k of t, isn't it? I think that is what is it. Okay. So I mean, we had seen this example for finding out what are the various strain quantities. Do you guys remember that a line element? So if I say that this is E1 and this is E2, so a line element along E1, it is not changing its length, right? It also does not change its orientation. But a line element along ET, its length is changing with time. Similarly, a line element along E3, that also does not change its length. Okay, so I hope you guys can recall it. Now let us see what can we say about the rate of change of those quantities, because that is what we are doing now. So we would like to find out this D tensor, let us say. What is D for this particular case? Okay, so remember that D relates the rate of change of line elements in the with rate of change of line elements per unit current length, and the orientation that goes in the formula, that's the current orientation, isn't it? For example, you recall that lambda dot by lambda is d times ny dot with ny, and these ny's are the current orientation, not the original orientation, or the one in the reference configuration. But notice that for line elements which are along E1, they always remain along E1, isn't it? For this kind of motion, the line elements which are along E1, they always remain along E1. Similarly, the line element which are along E3, they always remain along E3, isn't it? But what can you say about a line element which is at the current instant along E2? So how was this line element earlier? Was it also along E2? Can anyone tell me? So how was this looking like earlier? Inclined. In which direction? Forward or backward? Deflected backward from E2. That's true. So earlier it was backward, not forward. So if you want to see its evolution with time, then notice that here the y2 coordinate, that is not changing, because you see y2 is equal to x2. So y2 coordinate does not change. So if this is the line element, it has to remain in this, within this patch or strip. Basically the y2 coordinate is not changing, but y1 coordinate is certainly changing. So having uh, seen this, what you can say is that originally it may have been like this, and then at later time, so this is at time t, this is at t minus, and at later time it would become like this, t plus. Okay, so what can you say about its change in length at the current time, or let us say before the current time? What is happening to its length? Is it decreasing or is it increasing? What do you think? Anyone? So at t minus, what is happening to its length, rate of change of length? First decrease, then increase. That's true. So most of you have figured out correctly that at t minus it is decreasing, and at t plus it is increasing, isn't it? Because it has to remain in that strip, the top point at the top line and the bottom point at the bottom line, and then it is just getting inclined. So at t plus it is suddenly increasing. So what do you think about at t? What is happening at t at the current instant? Anybody? What's happening at the current instant? Zero. So that's a correct guess. That, I mean, if you think of continuity, initially it was decreasing, then it is increasing, so it must have passed through zero. So that means at the current instant, the rate of change of length must be zero, right? So let us try to see whether we can indeed, we are indeed seeing that or not. Okay. So of course, to get that, we have to first get the D. Okay, rate of deformation tensor D. And to get that, we have to first get the velocity gradient, Eulerian velocity gradient. So here is why this motion already prescribed. So let's first find out the velocity from here. So how do you get velocity? You simply take the time derivative, right? You see, it's a Lagrangian description. This is a Lagrangian description here. So getting velocity is quite easy then. So V1 is then simply k dot times x2, isn't it? And if you talk of V2, then it is 0, and V3 is also 0. Now, this is again the Lagrangian description of velocity. But to get the L, the velocity gradient, Eulerian velocity gradient, I want to write this in the Eulerian description, right? So k dot into x2. So how do I make it Eulerian? You see that y2 is same as x2. So that's quite easy here. That means v1 is simply equal to k dot into y2, and v2 is equal to 0, v3 is equal to 0. So we are very easily able to switch from Lagrangian to Eulerian. Okay, so having seen this, now let us think of this L. So let's try to find out the matrix of this L. So the components are del Vi over del Yj, right? Del Vi over del Yj. So that's going to be, so del V1, for example, del V1 over del Y1, that's 0. Del V1 over del Y2, that's k dot. Del V1 over del Y3, that's 0. And just all are 0. So that's the matrix form of velocity gradient tensor. So what will be D then? What do you think? What is D here? Just its symmetric part, right? So that's going to be 0, k dot by 2, k dot by 2, 0, 0, 0, 0, 0, 0. Okay? And then the spin tensor W, that's going to be 0, k dot by 2 minus k dot by 2, 0, 0, 0, 0, 0, 0. Okay, that's a spin tensor W. And from here, can you find out what will be the angular velocity W, the axial vector of this? So notice that it has just 1, 2 and 2, 1 component. This W tensor, skew symmetric tensor W has just 1, 2 and 2, 1 component. That means when you find out the axial vector, it's going to have only the third component. So first two are 0 and third will only be non-zero. And third one, if you follow the way we extract it, it comes out to be k dot by 2 with a minus sign. So that's the angular velocity. And when you talk of vorticity, it is simply 2 times of this, right? Okay, so now having found out this from the formula, let us see, is it matching with the, the physics that we saw earlier. So we figured out that line elements which are currently, okay, somebody is asking how to write D matrix. So D matrix is simply the symmetric part of L, right? Once you have L, you know that D is equal to L plus L transpose by 2. So if you think of the matrix, then D matrix is L matrix plus L transpose matrix divided by 2. Okay. Anyway, so now coming to the formula that lambda dot by lambda, that's equal to D times Ny dot Ny. So if you put Ny equal to E1, right? If the line element is currently oriented along E1, what do you get here? DE1 dot E1, isn't that D11, right? And that you can see that all the diagonal components are 0. So that means D E1 dot E1, D E2 dot E2, and D E3 dot E3, they are all 0. And first and last, we could find out easily, it's the second one where we did some physics, right? And you do see that it is equal to 0, right? So it's matching with our physics. Okay. What about, let us say, if we want to get shear strain, the change in angle thing, okay? So what is that going to be? Do you guys recall the change in angle formula? We had done it in the last class. So there was, of course, a general formula when the two line elements were not perpendicular. But suppose the two line elements are perpendicular. In that case, the formula had simplified, and we had that theta dot was equal to negative of 2 times d ny1 dot with ny2. So here, of course, ny1 is perpendicular to ny2. Okay. So when they are perpendicular, the formula was quite simple. So again, going to the physics, what do you think about the change in angle between line elements which are along E1 and E3? E1 and E3. So we had seen that the line element which is along E1 remains along E1. Similarly, line elements along E3 remains along E3. So the angle between them will also not change, right? So if you go to the formula here and put ny1 equal to E1 and ny2 equal to E3, then what you get is, so suppose I'll say ny1 is equal to E1 and ny2 is equal to E3. So in that case, theta dot is equal to minus 2 times d E1 dot with E3, and that turns out to be minus 2 times D31. Okay, now what is D31 here? So look at this, D31 is 0, and indeed from physics also that is going to be 0, right? So the formula is matching with physics. Now similarly, look at this part, D32 is also 0. That tells me that the change in angle between line elements which are currently oriented along 3 and 2, that's also 0 between 3 and 2. Can you indeed see that that should be the case, that the angle between line elements which are currently oriented along 3 and 2, that is 0? Anybody not able to follow this? You see the line element along E2 is indeed changing its orientation, but it's changing such that it remains in the E1 E2 plane, whereas line element along E3 is always along E3. So because the line element along E2 remains in E1 E2 plane, the angle between the two line elements will be will always remain 90 degree, and so theta dot will be 0. And that's why you're seeing that D31 is also 0. Sorry, D32 is also 0. But then the most important thing is the angle between line elements which are currently along E1 and E2. So that is indeed changing, right? The line element along E1 remains along E1, and which is currently along E2. You see that its orientation is changing. So the angle between them is suddenly changing. And that rate of change of angle is simply equal to D12. Okay, so D12, which is equal to also k dot by 2. Sorry, 2 times. So D12 is k dot by 2, but theta dot is negative of 2 times D12, no? And that turns out to be minus k dot. And can you see that why it is minus? So that tells me that the angle is decreasing. Okay, and indeed it should decrease, no? So you can see that from being in the black configuration at current time, it is going to red. So the angle between E1 and the E2 line elements is indeed decreasing, and that's positive shear. Okay, somebody was asking me yesterday also. So things are all matching with the physics that we have. Okay, let's do some more example. So this is of course problem 3.1 from the book. So it says that the velocity field for a continuum, so see I'm just saying continuum, which means it can be fluid or solid, is given by this formula minus alpha times y2 e1 plus alpha times y1 e2 plus beta times e3. Okay, so that's the velocity. So what will be the acceleration? So what you see is that the representation is Eulerian, right? Because velocity is written in terms of Eulerian coordinate. So what will be acceleration? So one thing is quite simple. Acceleration is simply v dot, right? And dot is the material time derivative. So take the time derivative everywhere, and you have minus alpha times y2 dot e1 plus alpha times y1 dot e2 plus 0. right? But y2 dot is same as v2. So this becomes then minus alpha times v2 e1 plus alpha times v1 e2. Okay. So and now you have v2. So this is v2 and this is v1. So you can put it back here, and what you have is then minus alpha square y1 e2 and minus alpha square y2 e2. Sorry, the first one is e1. So that's your acceleration. So we have gotten it back in the Eulerian form. So you see, this is from direct time derivative. But you could also think of using the formula. You remember what was the formula of acceleration in the Eulerian framework? So that was the local derivative del v del t, keeping y fixed, plus the velocity gradient, Eulerian velocity gradient, okay, grad of v with respect to y, which is L, right, times the velocity itself. Isn't it? That was the formula. So let us see if we are getting that. So maybe let's work it out in a coordinate system that is in E1, E2, E3. So acceleration is then del v by del t, which is the explicit time derivative. You see, keeping y fixed. Now from this formula here, what you see is that if you keep y fixed, then there's no time, there's no explicit time present. So the local acceleration term is zero in this case. Okay. What about the other one, the convective part? So for that, you have to get gradient of velocity with respect to y. So what will that matrix be equal to? So here you have first is del v1 by del y1. So del v1 is simply minus alpha times y2, and it depends on just y2. So you have 0, minus alpha, and 0. Then del v2 by all the coordinates with respect to all the coordinates, and that is here then alpha and 0, 0. And finally the del v3 by all the coordinates, but v3 is constant, so it is 0. So you see that this L, the velocity gradient, is already skew symmetric here. So d part is 0 here, okay, because it already is skew symmetric, multiplied by the velocity. When you write velocity in this coordinate system, you get minus alpha y2, then alpha y1, and beta. Okay, and finally when you work it out, matrix times vector, so what do you get? So first row into the column, and you have minus alpha square y1. Second row into the column is minus alpha square y2 and 0. And you can see that indeed this is same as what we got earlier. So you could directly do the time derivative or just use the formula. And directly using time derivative is not always possible, because it's only here that you had a simple representation for velocity. But wherever possible, you can do that. Okay, so that's one of the questions. And let me try to do some more. Um, so the next one, for example, is problem 3.2 from the book. So here it says that y1 is some cos of at into x1 minus sine of at into x2, and likewise y2 is sine of at into x1 plus cos of at into x2, and then y3 is x3 plus bt. So that's the motion. Okay, the kinematics is prescribed. So can you think of what kind of motion is this? Notice that when you put t equal to 0 here, you get y1 equal to x1, y2 equal to x2, and y3 equal to x3. So you get back the reference configuration. That means for this particular case, the reference configuration is also the configuration at t equal to 0. Okay, so this is a special case. It need not be always. So here reference configuration is equal to configuration at t equal to 0. Okay, so now can someone tell me what kind of motion is this? Okay, so Mano is already saying it's helical. Anybody else? Can you see that it is helical? Now, the way to see this is I could also write it as y1, y2, y3, that's equal to cos at minus sine at, then sine at cos at 0, 0, 0, 0, 1 times x1, x2, x3 plus 0, 0, bt. So the first part, you see what is happening in the first part. This matrix is also the matrix of rotation about E3. So the first part is simply going to lead you to what is called circular motion. You see, because the angle is rotation about E3 by AT. The angle is AT, which is changing with time. So the first part, any point x1, x2, x3 is following a circular trajectory because of the first part. Where the second part is simply also moving it along the axis, along E3, the second part. So there is circular motion together with a translation along E3. So that's why it becomes helical, isn't it? So that's why overall it's a helical motion. Okay. Now, if in this case I ask you to find out what is divergence of V dot, and let us say what is, so this is what the question is here. Um, Divergence of V dot, and the other one is divergence of velocity and then dot. What are these quantities? So let us try to see if we can find it. So of course we need to first get the V dot, which is acceleration. So we already have the Lagrangian description, right? This is Lagrangian. So getting velocity and acceleration is quite easy, you know. Just take the time derivative, keeping x fixed, or you can also see from here. So having seen this matrix form, you can also write it as, you know, in tensor form. Y is equal to this rotation big R times x plus BTE3, isn't it? So what is then y dot? Y dot is then simply R dot times X plus B of E3, right? And this is then R dot R transpose into R into X plus B of E3. And R dot R transpose, you can recall, that's the W and Rx, and then you have Rx, okay? So Rx is simply Y minus BTE3, okay, plus BE3. And then this is also equal to W cross product Y minus BTE3 plus BE3. But notice that what is the W here? So this rotation is the rotation about E3 axis. So for this rotation about E3 axis, the big W tensor or the W vector, it's simply because we know that it's rotation about E3 axis. So the angular velocity corresponding to it is rotation about E3 axis. Okay. So can we say that small w is simply A times E3? Small w is A times E3. That's the angular velocity because it's rotating about E3 axis, and at what rate? Theta dot, that is A. Theta is 80, so theta dot is A. See, we can also derive it actually. Let's try to derive this. So big W is R dot R transpose, no? So when you, for the given R, when you do the dot, so look at this given R, you do the dot, you have in the argument 80, so first it was cos, so that becomes minus sine of 80. Then you had minus sine, that becomes minus cos 80 and 0. And then you have sine of 80, that becomes cos of 80. And then cos of 80, that becomes minus sine of 80, 0. And then you have 0, 0, 0. And you see, you also need theta dot, which is, so you get an A outside, multiplied with R transpose, which is cos sine 0 minus sine cos 0, 0, 0, 1. Okay. And when you work out this rotation, this multiplication, it turns out to be 0, then minus 1, 0, 1, 0, 0, 0, 0, 0. Okay, when you work it out, you will see that it is indeed A times this skew symmetric tensor. So that's your W. Okay, that's your W skew symmetric tensor. And from here, you can see that this W vector, the axial vector, is simply 0, 0, A. Okay, so coming back, this W vector is AE3 cross product Y minus BTE3 plus BE3. So that's simply AE3 cross product Y itself plus BE3. Okay, so that's your velocity. Now it's written in the Eulerian form, velocity. So what is an acceleration? And you see the form of velocity. It has also a component. So this part is the velocity term which is in the E1, E2 plane, because it has to be perpendicular to E3, right? AE3 cross product Y. So it has to be perpendicular to E3. So the first term is the component of velocity in the E1 E2 plane, which is leading to circular motion. And the second term is the component of velocity along E3, because of which it is becoming helical. Okay, so this being the velocity, then you can also find the acceleration. So acceleration, you know that, because you have an Eulerian form, so you simply say del v del t plus del v del y, and then multiply this, or I could also put it right in the tensor form, del v del y multiply with the velocity. So the first term is of course 0 here. You can see that it has no explicit time derivative time present here in the Eulerian form. So the first term is 0. The second term, we need del v del y. Okay, so here you could also see that this is same as w times y plus be3, and therefore the gradient of v with respect to y is simply that w. Okay, so we can come back here and write that this is equal to w times v, which is the angular velocity w cross v. Okay, so now you can then write it as AE3 cross product velocity, which is AE3 cross product y plus BE3. Okay, so things are getting simple now. So this is equal to EE3 cross product EE3 cross y. Okay, and then you have to use the formula of A cross B cross C, which is simply EE3 of AE3 dot y. So remember this formula, A cross B cross C, that's equal to B A dot C minus C A dot B, back minus cab. That's how I used to remember, back minus cab. So I use this formula, and that is the first term minus y of AE3 dot AE3. So AE3 dot y, so that means we just need the third component of y, so that's y3. So we have y3 times a square e3 minus a square y. Okay, that's the acceleration. And once you have the acceleration, the question was to get divergence. So what's the divergence of acceleration? Gradient dot a. But a is a constant here. So gradient dot a will be 0. Also a is a scalar. So how can you take the, okay, so some of you are saying it is 0. Is it indeed coming out to be 0? So for this part, obviously the divergence, the Eulerian divergence is, so I should say here divergence of a square y. How much is this part? So a square being a constant comes outside, and then you have a square times divergence of y. What is this equal to? Divergence of y, and notice that divergence is with respect to y itself. It's 3, yes. So this part is 3 times a square. And what about this part? So this is a square y3 e3. And when you take its divergence, what do you get? So that part is not 0. For the first term, what is the divergence of it? So basically this is equal to a square into divergence of y3 e3. Yeah, so divergence of y3 e3 is simply 1. So here you get a square, and the second term is minus 3a square. So what you have here is minus 2 times a square. Okay. To find divergence, you can use the formula that we had mentioned earlier. So for example, this divergence of any vector v is del v over del yj, and you put a dot here, ej. That's the divergence for a vector. So if you just try to do it for, let us say, when you put v equal to y itself, then you have, for v equal to y, you have del y over del yj dot with ej, and then you write y as, let us say, yi ei, so it becomes del yi ei over del yj dot with ej. So this is same as del yi over del yj ei dot with ej. So that's del yi over del yj into delta ij, which is del yi over del yi itself, right? So you have del y1 over del y1 plus del y2 over del y2 plus del y3 over del y3. So each of them giving 1. So total is 3. Okay. So that is, so there are several examples, several more examples, of course. So I'm going to stop the class here, and you are now free to ask me questions.
This big W tensor into vector Y is equivalent to the vector small v, small w cross Y. How are these two
Yes.
equal?
Okay, this is something we have already done earlier, no? So whenever you have a skew symmetric tensor W, see this works only when W is skew symmetric. So for a skew symmetric tensor W, times with any vector, let us say A, that's equivalent to the axial vector of this skew symmetric tensor W cross product A. And this axial we are writing as the vector W cross A. So this is by the definition of axial vector. You can write it like this. So you see, if you form your W like this, 0 minus W3, W2 minus W1, 0, W3 minus W2, W1 and 0. Okay, let us say your W skew symmetric is this, and I multiply this with A1, A2, A3. Then what you get? You will get um, W2 into A3 minus W3 into A2, right? And the second one will be W3 into A1 minus W1 into A3. The third one will then be W1 into A2 minus W2 into A1, right? But you will notice that this is also equal to W1, W2, W3 vector cross product A1, A2, A3. So when you do this cross product, you will get the same thing. So this thing here, that's the axial vector of this skew symmetric tensor W. Okay, see this part is the 1 2 component here. So 1 2 component 3 is missing, so this goes in the third component of this axial vector. This part is 1 3 component and 2 is missing, therefore whatever is present here goes in the second component of axial vector, and likewise. But basically, essentially it is this: when you see it skew symmetric time tensor times any vector, you can write it as a cross product. Okay, any other question?
Sir, in problem 3.1, the previous problem, we have taken the Eulerian form it is given, and to find out the acceleration we have taken with respect to derivative with respect to t directly. Yeah,
Yes.
this only. So are we allowed to do that? I mean, normally in Lagrangian only directly we take with respect to t keeping x fixed. So in
Exactly.
Eulerian
So
form
here
also,
also, see here also, although it's an Eulerian form, but when you are taking the time derivative, we are doing it keeping x fixed. Okay, so when you do that, you come to the right hand side and you know what are the things which are dependent on time, and then you take the time derivative keeping x fixed. So when you do del y2 by del t keeping x fixed, it is actually v2 then.
okay, okay. So it need
Yes,
not be then like y2, y1, and this need not be explicitly put in terms of x1 and all while taking a derivative even
exactly.
in Eulerian form.
That's true. That's true.
Okay. Yeah, for more special case, say uniaxial stretching, so we have written. So here, how we reach to this expression is like e1, e2, e3 are basis vectors and perpendicular. So accordingly, we added and subtracted. So we got I here and lambda 1 minus 1 and e1 tensor product e1. But then
Right.
when we have gone for general uniaxial stretching, sir, so E1
Yes.
directly we have changed to any normal n. But there
Yes.
we are imposing this condition that whether this different set of n1, n2, n3 vectors would come into picture, or directly E1 alone we can change it to n. Then I will not be of that form, no? Because to
See,
get I,
I tensor. Yeah. Okay. So I tensor, identity tensor is always diagonal in any coordinate system. I is always diagonal in any coordinate system.
so here also then inbuilt it is there that when E1 we are changing to n, so accordingly E2 and E3 also will be changing to a different coordinate system.
No, no, no. It's not like that. See, we are not doing any rotation here. I'm just saying this formula that we have. So this formula, it tells us that it is a case of uniaxial stretching along E1, right?
Yes, yes, sir.
And from here, we got a cue that if the uniaxial stretching is along N, then it should be of this form. See, you can also, for example, actually do it and see. So suppose I take lambda, stretching lambda, no? So lambda, or maybe like this. We know that dy is equal to f dx, right? Dy is equal to f
Yes.
dx. So if I take dx to be along n, okay, then let us see what we are getting. If I take dx to be along n, then for this particular form of f, I have identity plus lambda minus 1 n tensor product n multiplied with some n into scalar dx. Okay, scalar dx is the magnitude of that line element. And when you work it out, what you get is the first term identity into n is n itself, so that is n dx, right?
Yes,
Plus
sir.
the second term, see it's a second order tensor multiplied with n, so you have to dot it, so n dot n is 1,
One.
and then you have n itself, so it is lambda minus 1 into n dx, and you add it together, you get lambda times n dx. So indeed you see that this deformation is such that for line elements along n, it is becoming lambda times the line element. So it is indeed a stretching. But if you choose any other line element which are perpendicular to n, okay, so suppose I redo the same thing, but taking n to be some n perp, any line element perpendicular to n, so I am denoting that by n perp, okay. So when I work it out, it becomes n perp dx plus the second one you see n dot n perp, that is 0, right?
Yes, 0.
And therefore it gives you 0. So what you see is that all other line elements which are perpendicular to n, they are unchanged. And isn't that the case of uniaxial stretching?
Yes, sir. Yes.
So
Understood, sir.
that's why, yeah,
Also, sir, when we do the linearization of our volumetric strain, that dV upon dV not equals to that of F
yeah,
we are doing. So
yeah,
there already it is in the determinant form, and like
yeah,
what will their linearization means actually inside F whatever like U terms are there, their linearization, because here there is no vector form and all. We will get directly a value only determinant. So whether that
right,
will change with respect to linearization or it is going to be same only. Like all other things we had in terms of, I mean, we were writing F transpose F and then F we were changing I plus
yes, yes, I
del U.
understand. I understand what you're saying. Maybe let me try to do that and show you. So basically, you are saying how to do that linearization, right?
Yes,
So
yes,
determinant of f, which is equal to determinant of identity plus grad u, right?
yes, yes.
So yeah, this is not so easy, of course.
Because there is no power and other things coming and no higher order terms and also how to.
Yeah, yeah. I think for these kind of problems, either you expand it, okay. You can. I also see if I can do it in some tensor form. I'll try to see it. But of course, one of the ways that you directly write it as a matrix as 1 1 1 and then plus del u 1 by del x 1 del u 1 by del x 2, so you populate it and then work out the determinant, okay, and then neglect the higher order term and keep only the term up to the first order in u, and you
Leading
will see
order.
that, yeah, leading order, and you will see that it becomes 1 plus del u 1 by del x 1 plus del u 2 by del x2 plus del u 3 by del x3, which is 1 plus divergence of u, and that's the Lagrangian divergence.
Right. Like when we have to prove that in case of say uniform material particles forming straight line, it will continue to form straight line only. So like whether we have to show that angle between the two is not changing, something like that, or we have to, because with one we do not have any reference, no, so we need
Yeah,
to have
yeah, yeah. That's
the angle we have
see,
shown.
what you have. So see, when you have to prove that you have a deformation such that finite lines also remain finite, right? That is the thing, no? So in that case, you have to take here you have to represent this line as some, let us say you choose here x naught and the direction is t. So this x is then x naught plus some parameter which varies along this line. let us say I denote that by epsilon into t. So that's the vector form of the straight line in the reference configuration. And you should show that it becomes, finally, after deformation, it should become some y naught plus epsilon times some ty, something like that. So that's a direct proof that, okay, a straight line has indeed remained a straight line.
Okay, so it has rotated, but like the shape is still straight line only, like that.
Right, exactly. So, this is also not difficult. For example, so in case of homogeneous deformation, you are saying, no?
Yes, sir. Yes.
So this f is constant, so therefore y is equal to f times x, right? For a
Yes, sir.
constant f. So let us say I make it f naught. Now put your x equal to this here. So it becomes f naught into x naught plus epsilon t, which is equal to f naught x naught plus epsilon times f naught into t, right? So you can
Yes.
directly identify that this part is y naught and this part is ty. So it is still in the form of a straight line. This is denoting a straight line. So straight line remains a straight line, therefore.
Like in case of straight line, we have assumed an equation, but when it
Yes.
is like plane or ellipsoid, that will be difficult to show, no? In this
No,
case,
so
or
again for ellipse you have to again take the equation of ellipse.
okay, okay.
Yes.
Then plane means I think some area we can take, cross product we can take to show a plane remains
Okay,
plane.
for plane, so any point on the plane, I think there's a formula for vector formula for plane also. So x, I think x dot n is equal to d. I think there's something like that. That formula x dot n is the constant d. So all those x satisfying this constraint are the planes which they lie on the planes whose normal is n and its distance from the origin is d. So that's the formula for the plane. And then you have to show that whatever y you are getting still has a similar, for some different n and d, you get a y.
Okay, okay. It will
Yeah.
remain plane, but normal and the distance will change. So
Yes, exactly, exactly.